Okay, so our second talk today is by Rachel Skipper. And well, what will you talk about?
Yeah, so I'm talking about maximal subgroups of Thompson's group V.
Okay,
Um,
yeah, please.
Thanks for the introduction and for the invitation to the seminar. Yeah, so everything I'm talking about today is joint work with Jim Belk from Glasgow, Collin Bleak, and Martyn, who are both at St. Andrews. Um, so the focus of the talk is really going to be on a specific group, and that is Thompson's group V. So historically, the place the Thompson group showed up first was in 1965 when Thompson introduced three groups at the time. These groups are now generally referred to as F, T, and V. And he introduced these in some handwritten notes that never ended up actually published. And part of his motivation for introducing these was to produce possible counterexamples to the von Neumann conjecture. Just to remind you what the von Neumann conjecture says, is it says that a group G is amenable if and only if it contains, is non-amenable if and only if it contains a free subgroup. And so even, this very initial introduction of these groups had to do with interest in understanding what subgroups they have. The von Neumann conjecture is now known to be false, of course, so it's false due to examples by Olshansky. But it turns out for F, it's a much harder question. So it was a difficult theorem of Brin and Squire in the 80s to show that Thompson's group F does not contain any free subgroups, although the other two groups do, T and V. So T and V both have free subgroups in them. But yeah, it ends up being one of the, really difficult questions in group theory is solving whether F is an amenable group, right? This is one of these dangerous questions in group theory where there's, been many attempts over the years by very strong mathematicians, and then there's been close proofs, but never a full proof seems to arise. And so, yeah, this remains one of these sort of widely open questions that you tell your grad students not to work on, like it's. On the other hand, yeah, F, as I mentioned, T and V do both contain free subgroups, and so they are in fact non-amenable. But moreover, one of the things that Thompson showed at the time was that they are both finitely presented and simple. And at least in my mind, I find it sort of shocking that these, in fact, are the first examples that we had in the case. Yeah, so I should add the word infinite here. These were the first examples of infinite, finitely presented, and simple groups. So again, like this thing that Thompson was proving was a statement about subgroups of T and V, right? That they have no non-trivial normal subgroups. Yeah. And still, we know relatively little about what the world of infinite simple groups can look like. This is always a fact I find sort of baffling, given the fact that for finite simple groups, we know all of them, right? We have a list, yeah. But the world of even finitely presented infinite simple groups is still quite mysterious, and a lot of the progress in understanding infinite simple groups comes from studying these two initial ones that Thompson
Well,
introduced.
if I can maybe briefly interrupt, right? I mean, as we know, the list of these finite simple groups is quite lengthy. So maybe it's
Yes.
not a surprise that,
Yes, and it was quite a bit of hard work to get there, right? As well. It was, one of the largest collective efforts in mathematics, right? Was getting this list. Yeah, so it's not, yeah, even in the finite case, it was non-trivial. But it still feels like in the infinite case, we're very much just still coming up with examples, rather than having anything close to some general theory of what these things should look like. But that's right. Yeah. Yeah. I shouldn't downplay how hard the finite simple groups are. Yes. Extremely difficult objects as well. Right. Yeah. Okay. So we do know quite a bit about what things can embed in V. So V is going to be the main group I'm talking about today, although T and F will show up periodically throughout the talk. But in terms of things that we know already that embed into V, so wide variety of subgroups of V. So for instance, V, this did not come out very well. Okay, so V contains S infinity, and hence it contains all countable locally finite groups. So I mentioned this because one of the sort of motivating ideas when you're thinking about Thompson's group V is to think about it really as being, um, a type of infinite permutation group. So V has many characteristics in common with finite permutation groups, and this is often a motivating sort of ideology that helps one come up with what one should expect for V. So yeah, later I'll formally define V, but yeah, that'll come in just a little bit.
So
And there you'll be
S-infinity
able to see
is
this.
just the permutation group of some countable set, or what is S-infinity?
V is, yeah, oh yeah, yeah, that's what I mean, is the permutation group of a countable set. S infinity is the permutation group of a countable set. Yes, exactly.
Only finite support permutations, though.
Yes, finitely supported. Yes, thank you, Billy. Yes, yeah, that's important as well. Finitely supported. Yes. V also contains all finitely generated free groups, all finitely generated abelian groups, Houghton's groups, arbitrary direct sums of copies of itself, so it has some sort of fractal-like structure to it as well, which again makes it sort of amazing that this group ends up being finitely presented, given that, it's in many ways made up by these big direct products of copies of itself. And sort of the motivating question for us then is, what obstructions are there to a particular group embedding in a Thompson group? Another place where this has been showing up quite a bit lately. So at this point, there are many variations on the Thompson groups that people have built. And one of the questions where this is showing up is what's called the Boone-Higman conjecture, which is a conjecture from the 70s about what groups can embed in a finitely presented simple group. And so far, most of the progress, again, has been constructing Thompson and Thompson-like groups and trying to figure out if a particular group can embed in one of these objects. Yeah, but there are some things that can't embed in Thompson's group V, and in particular also not in F or T. So some things that can't embed. So Higman showed that any element of infinite order has only finitely many roots. And a consequence of this then is that, so this is a statement about V. So any element of V of infinite order has only finitely many roots. And so what this means is, for instance, things like Bohm-Slog solitaire groups will not embed into V. Other things, some words we saw earlier today. So V is also a torsion locally finite group. So Gororchik's group, for instance, does not embed into this group because it has, it is itself an infinite torsion group. Whereas any torsion subgroup of V is in fact, any finitely generated torsion subgroup of V is in fact finite. Also, in the case of infinite order elements, Blake and Salazar-Diaz ended up sort of surprisingly showing that the free product of Z squared with Z also does not embed in V. But again, these are sort of just general examples that we have. Another reason why one might be interested in studying maximal subgroups of, whatever your favorite group is that, and whenever your group is finitely generated, then it's a general fact that every subgroup is contained in a maximal one. So in particular, if you have a group that's described in terms of some action on some space, you might want to ask, for instance, questions like, does V contain some proper subgroup with some dynamical property, say, right? Because V is going to be defined in terms of dynamics on the Cantor set. Or, whatever group you have, is there exists some proper subgroup that has sort of, has some geometric, dynamical, topological property. The question that sort of started this project, for instance, is that it turns out that V is dense in the group of homeo of the Cantor set. And we were wondering, does V have proper subgroups that are dense also in homeo Cantor set? It turns out, yes, it does, and not so hard, it turns out, to find such things. But yeah, if you're interested in knowing whether a proper subgroup has such a property, I mean, especially if it's some property of the action, then you might as well be looking at your maximal subgroups and just considering, the smaller class of subgroups. Moreover, maximal subgroups also have this great property that they correspond to primitive group actions. So again, yeah, so if we think about primitive group actions, these primitive group actions, what they are is they are really, these are the building blocks of group actions. So yeah, so more precisely, an action of a group G on a set is primitive if it preserves no non-trivial block structure. And so what this is telling us, right, yeah, is that, we have, again, if you have some group and you want to understand the way it can act on spaces, what are the restrictions for types of actions that can occur? Well, you really want to understand all actions, and primitive actions are sort of your starting point for understanding these. And yeah, the way this works, the reason that maximal subgroups correspond to primitive group actions is, an action is primitive if and only if the stabilizer of the point is a maximal subgroup. So one way to sort of think about this is if you think about the way the group acts on the cosets of the maximal subgroup, this is going to be primitive. Yeah, so in general, if you're acting on the cosets of a subgroup, this is going to be primitive if and only if the subgroup is maximal. So if you're able to study all maximal subgroups, then at the same time, you're able to possibly induce information about, what types of actions the group can have. All right, so I've tried to give a little bit of setup here, but I think one downside with this talk that I have given is that it takes me a while till I get to actually defining Thompson's group, but we are there now. So let's define what Thompson's group V is and why, why understanding dynamics is sort of the right thing here. So Thompson's group V is defined via an action on a Cantor set, but we're going to build this up in a few pieces. So I'm going to take X to be the set 0, 1, X star would be the set of finite words over X, and X omega to be the set of infinite words over X. And given the theme of the seminar, probably you all know where I'm headed with this, is that, this lets you build this binary rooted tree. And the boundary of this rooted tree is exactly these sets of infinite sequences, which exactly we can think about as being the Cantor set. All right, so V, it turns out, does not act on the tree, but it does act on the boundary of the tree. And to build this action, we first want to talk about something called cones. So for a vertex in the tree, we define the cone at V to be the set of infinite words, the set of points in the boundary that have V as a prefix. So the image here, right, you have your tree. Let's say this is your vertex V. Then the cone is all these points in the boundary. One way to think about the cones in terms of, just the Cantor set is the cones are, just your basic Clopin subsets. So when you, take your standard basis for the topology on the Cantor set, it's exactly going to be the basis consisting of these cones. All right, so then the way we build elements of V is we first take two partitions of, so I'll call these two partitions U1 through UT and V1 through VT. These will be two partitions of the boundary or of the Cantor set into cones. And whenever you have such a set of partitions, then you can define this prefix replacement map, where what I'm going to do is I'm going to take anything that has the prefix UI, and I'm just going to replace that with the prefix VI. So you just cut off the prefix, replace it with the other prefix. And so we tend to call these prefix replacement maps. Right, so a prefix replacement map just comes from choosing two partitions. You need the same number of terms in each partition, and then you just define this map where you remove a prefix, you replace it with a different prefix. All right, and now we can define Thompson's group V in that Thompson's group V is just the set of all such mappings. So the set of all such ways you can divide the Cantor set twice into cones and then do this prefix replacement map. Okay. There's a second definition of Thompson's group that I find often more convenient, and we'll want to sort of go back and forth between these two definitions. And the second definition comes from something called strand diagrams. So I'm not going to write the formal definition. We're going to do definition by example, but I think generally it's fairly clear, but feel free to stop me if it's not. So the idea here is what you're going to do is you're going to choose, your prefix replacement map. So let's say we take 0, and we're going to map it to 0 to 0, 1, 1, 0 to 0, 0, and 1, 1 to 1. And then to do our strand diagram, we're going to build 2 trees. So the first tree is going to have the property that you're going to have its leaves be the codomain cones. And so, so I have this tree here, and I have my leaves being labeled by 0, 1, 0, and 1, 1. And similarly, right, I have my codomain. Yeah, so this is my domain tree. I'll have a matching codomain tree. So here's my codomain tree. So with 0, 0, 0, 1, and 1. And then the only thing that's missing from this tree pair that to complete the description of the element is I just need to tell you which cone is being mapped to which cone. So 0 is getting mapped to 0, 1. So all I really need to do is draw a connector there. And 1, 0 gets mapped to 0, 0. So I draw a connector there, and 1, 1 maps the 1, and I draw a connector there. Okay, there's one little subtlety though when we talk about these tree pair diagrams. One thing that we have to be a little bit extra careful about, which is the fact that there is not a unique tree pair diagram or not a unique strand diagram that represents a fixed element of Thompson's group. The way to see this, right, is imagine I take one of my cones and I divide it in half. So 1, 1, 0, 1, 1, 1. And I divide the matching codomain cone in half. And if I map the left half to the left half and the right half to the right half, I've done the exact same function on the Kenner set, right? But this is going to give me a different tree pair, and the tree pair it's going to give me corresponds to adding an extra caret here and adding an extra caret here, and then just connecting the left to the left and the right to the right. So when I give this second definition of Thompson's group, I really have to say it's not just strand diagrams, but it's the set of equivalence classes of strand diagrams.
Can I ask a quick question? I mean, I somehow remember there was some other definition related to these Thompson groups based on piecewise linear functions on dyadic intervals.
Yeah, that's right. That's right. So yeah. So let's see. So yeah. So right. So let me add in something here and mention. So yeah, because this will be relevant later to define what F and T are. So yeah. So generally, again, remember we have these 3 groups, these 3 Thompson groups, F, T, and V. So V is the main focus, but F and T are going to show up today. So it's worth mentioning formally how to define these. So usually you think about F as acting on the unit interval, T acting on the circle, and V acting on the Cantor set. And so the way this works, right? Yeah, so F, so if I take these same types of tree pair diagrams, and then, yeah, let's see, we have this one here. Okay, so the one here that we've drawn first, this is the one that lives in V. But for one to live in F, you have to, the requirement is you have to preserve the linear order on leaves. Okay, and so what that means is once I have the tree pair, I only have one choice. The first one has to go to the first, the second one has to go to the second, the third one goes to the third. And one can use this to get a description, in terms of piecewise linear homeomorphisms of the unit interval. And the way this works is, well, this vertex was the vertex 0. So I'm going to think about that as being the subinterval 0 to 1/2. And the second one here is going to be 1/2 to 3/4. And the third one here is 3/4 to 1. And then I do the same for my bottom, and then I'm just mapping these intervals to these intervals. So this is what F is. And then T has the property that T has to preserve the cyclic order. All right, so what that means is I'm allowed to do something like this, like I can send the first one to the second one, but if I do that, then this one has to go to the next one as well, and the only option then is here. And so this is how you get this description of T as acting on S1. Instead of giving a piecewise decomposition of the unit interval, it's giving a piecewise decomposition of the unit circle. But using this tree pair diagram, using that standard definition of F as piecewise linear on 0, 1, T as, these piecewise linear on S1, and V acting on the Cantor set, the standard definitions don't make it obvious that one's included in the other, but these strand diagrams do, right? Now you can see exactly how one sits inside the other. Yeah, good. Are there any other questions?
Yeah, thanks. That was actually a very nice explanation.
Yeah, okay. Yeah. And it turns out also you can define multiplication totally in terms of these strand diagrams as well. So basically you just take two of them, you put them next to each other, you add carets as necessary so that the bottom tree of the first agrees with the top tree of the second, and then you just erase those trees and stack your picture. And so that's one really nice thing about this description as well, is it is in fact a full description of the group, right? It includes the group law as well, right? How to multiply. Yeah. All right, but yeah, so the reason we want to look at these strand diagrams is, and this description is because in particular, again, we're after these maximal subgroups. So the place to look for them is by finding, group actions. And this description of V, in fact, so V, we know it's acting on the Cantor set, but this description of V, in fact, gives a partial action on the set of cones. It's only a partial action because there are going to be some cones that might get mapped to a union of cones. And so there will be some cones that don't have a well-defined cone image, but there are only finitely many of those. And so this is why we say partial, right? It means that it's an action up to a finite set where they don't actually have a very nice, well-defined image. And so, yeah, the way we're going to think about this action on cones is, again, thinking about cones as coming from vertices of the tree. And so then we have, given, alpha and beta, we'll say that an element maps alpha to beta if the cone at alpha is mapped to the cone at beta via a prefix replacement. So this is sort of a subtle thing. Yeah, so the idea is you could always, in the way we subdivided our cones and map the left to the left to the right to the right, one thing you could do is subdivide a cone and map the left to the right and the right to the left. And I don't want to consider that the group action, if that makes sense, right? It's still mapping the cone to the cone, but not linearly. So I want to only say the group acts taking alpha to beta if it takes that cone linearly to the cone beta. Anyway, for this talk, it probably doesn't matter so much, but it is one of those little subtlety things that you have to deal with when you're doing this stuff. So then, with the notion of this partial action, we can also come up with some notion of what it means for a partial action to be primitive or imprimitive. Remember, full actions are primitive. Full actions are imprimitive if they preserve a block structure. So we want to say something similar in the partial action case. We want to say that the action is imprimitive if it preserves some block structure, which is really just the same as saying some equivalence relation. And so what is, but an equivalence relation is just a labeling of the tree by some colors. Yeah. So two vertices are equivalent if they're labeled with the same color. All right, but for an arbitrary labeling of the tree, it's not going to be compatible with the action of V. So again, it's exactly because of this ability we have of adding carets, right? And maintaining the same element of V. And so because of that, we want to restrict our attention to what we call type systems. So we say an equivalence relation is a type system if alpha is equivalent to beta, if and only if I add an extra 0 to the end of alpha and an extra 1 to the end of alpha, that's going to be equivalent to beta 0 and beta 1. All right, so meaning, yeah, and so what that means then is these type systems are going to be precisely the equivalence classes that can be described using, say, some finite set of, in the finite case, it can be described using some kind of finite set of building blocks. And what I mean by that is, so I'm always going to have, when I do this setup, I'm always going to have this like distinguished top block. All right, so because I always have my full counter set here, which is distinguished. And what this says is I should label the left by red and the right by green. But now I go back and I look at my list of pieces that I have here in my toolkit. And so here I see my red piece at the top. And so red says I should have red below it on the left and blue below it on the right. And similarly, I go back to my list and I see my green block. My green block says I put another green on the left side and I put a blue in the middle. I go back to my blue block. My blue block says whenever I see a blue, I see two blue below it, right? And so what I'm trying to indicate here is that these four pieces is enough to tell me fully how to label the tree. And this is what these type systems are going to come from, right? Is having some building blocks that tell you that every time I see a blue vertex, I should see two blue vertices below it, or every time I see a green vertex, I should see another green vertex to the left and a blue vertex to the right. And these are going to be the labelings of the tree that are really compatible with the action of V. All right, so yeah, so a lemma is that if you have one of these type systems, one of these equivalence relations, and it's neither the trivial relation, meaning every vertex is labeled by a different color, or the universal relation, meaning every vertex is the same color, then if I consider the set of elements of V which stabilize this equivalence relation, this is going to give me a proper subgroup of V. Right? And again, our goal is really to get to the maximal case and understand when these are going to give us, in fact, maximal subgroups. In order for us to understand when these are going to give maximal subgroups, the first thing we do is translate the question to a question about graph theory. Yeah, and again, this is going to be sort of a definition by example, but the idea here is we're going to build a directed graph that corresponds to the equivalence relation by just quotienting the tree by the equivalence relation. So example, if I take the slope a power of 4 subgroup, all right, so what this means is, yeah, I'm alternating levels of the tree with my two equivalence relations, my two equivalence classes. And what this says is I have to preserve whether a vertex is on an even row or an odd row. So if I quotient this, then the thing I get out of it is a graph that looks something like this, right? And this is what we're going to refer to as the type graph. We're going to want to think about this as a directed graph, again, with our distinguished vertex corresponding to the root of the tree. And so all things are emanating out of this one vertex.
So can I ask a quick question?
Yes, of course, yeah.
It looks to me like the root node is a different color than anything below, but
Yeah.
it has the same, so it looks like there is every green node has the same children as this root node, yet the root is not green.
Yeah, so when I do this equivalence, really, yeah, okay. So this is maybe
it seemed that
right.
you were saying that it's an if and only if that the children determine the root and the other way.
Sure. Yeah, yeah. So yeah, maybe I should say that the root vertex is always going to just be our distinguished. I can think about the root vertex as being colored the same as the others, but I want to distinguish it. So yeah, so I should clarify it in the type system thing. The root, yeah, is the only exception here. And this is just because you can never map the counter set properly inside the counter set by V, right? The counter set has to get mapped to the whole counter set. So it is a cone. It's the cone corresponding to the empty word. But yeah, for any of this to make sense, we always do have to actually distinguish the root vertex. So you're right. Yeah, maybe my definition of type system is brushing something under the rug there, which is that I do want to separate out my root vertex as being different than anything else.
Thanks.
Yeah, of course. Yeah. All right. So yeah, so now it's this question about, directed graphs, right? What can we say about these directed graphs? And so, yeah, so we'll say that a type system is simple if it's only proper type system quotients. Quotient is the universal relation. So meaning, right, if I glue together two of my equivalence classes and then I do whatever I need to make sure it's still a type system, then the only possibility I get is the relation that everything is identified. So if that happens, we say the type system is simple. And so again, yeah, and this is really the reason we want to look at the graph setting is because you can understand quotients of graphs, right? Quotients of graphs are something that, you can see, especially taking advantage of the fact that these are directed graphs. And so the first thing we show is that if you take a finite simple type system graph, then basically there are three options that can occur. So the first is what we call nuclear. So what nuclear means, so again, I'm always going to have this distinguished root vertex. And nuclear says that, I have some paths coming out of my root vertex. But after some finite amount of time, so fixed finite amount of time, I end up in some portion of the graph where what I want is that this graph has the property that it is highly connected. Meaning I can get from any vertex to any other vertex in this component, and inescapable. Meaning I can never get out of this. There's no, thing coming out, right? So this is what we call nuclear. Yeah, so this is the first type that can occur. The second is binuclear, with nuclei of size 1. All right, so this is similar, right? That after some finite amount of time, I'm in a nucleus, but I am only going to have 2 nuclei. So again, nuclei here just refer to highly connected and inescapable subgraphs. And so, yeah, so what that means, right, for these, but these are only, they have size 1. So that means the only option is I'm going to have 2 edges, both circling back to these. Yeah. So after some finite amount of time, I'm stuck at one of these 2 vertices, and I never escape those 2 vertices. And the third possibility that shows up when you're trying to analyze quotients of these graphs is something called atomic quasi-nuclear. So what this is again, after some finite amount of time, I end up in something that looks like a nucleus, meaning it's still highly connected. So highly connected. But it is escapable, but only in one particular way, meaning I have one extra vertex that I can sometimes escape to. But once I'm at this one vertex, I'm stuck here. So this vertex here is the unescapable bit. All right. And yeah, so these are, we get these 3 types of graphs. And again, it's, not a complicated thing. It's just trying to understand what quotients of these graphs are going to look like, right? But what we're able to show is that whenever you have a simple type system of one of these 3 types above, then the stabilizer is in fact a maximal subgroup of V. So this proof ends up being sort of a case-by-case analysis of these 3 cases. But there's, again, a little bit of subtlety, which is worth mentioning, is the classification we have of simple type systems is in the finite case. So this theorem is in the finite or infinite case. So meaning we're able, one can build infinite, for instance, infinite atomic quasi-nuclear things. And if you take an infinite atomic quasi-nuclear type graph, it's still going to give you a simple type system. So one question that's still here is, are there infinite simple type systems that don't look like one of these three, for instance? Right? And in that case, do those give you maximal subgroups? Like this is, yeah, so this is something, for instance, we don't know. All right, but in each of these cases, we can actually say something about what these subgroups look like of V. So, in the atomic quasi-nuclear case, so again, so I'm working now backwards in the theorem just because it's easier to look at these here. So if I look at the atomic quasi-nuclear case, meaning I have this one vertex I'm allowed to escape to, what you end up with is finding the subgroups of V, which correspond to stabilizers of finite collection of rational points in the Cantor set that all have the same tail class. So meaning you're looking at sequences which eventually repeat, right? They eventually have some period to them. And you want that the collection you're looking at have the same ending periodic piece. So these are the maximal subgroups that were generally known before any of our work, right? It's sort of a folklore result that stabilizers of rays are going to give you maximal subgroups. So this is a slightly upgraded version of that, saying that you can also have stabilizers of finite collections if they have the same infinite tail class. And this is basically because you're going to be able to also be very transitive on the rays, right? You'll be able to have an action that permutes the rays around as well. And the multinuclear with two nuclei of size 1 case, what you end up with is a stabilizer of a partition of the Cantor set into finitely many Clopin sets. So in other words, you sort of imagine, you sort of take your, something that could occur here, maybe the most basic thing is that on one side of the tree, all you ever see is green vertices. And on the other side of the tree, all you ever see is red vertices going all the way down. And so this is giving you something that looks like V cross V semi-direct product, the symmetric group on 2 letters. So these multinuclear with nuclei of size 1 are giving you, this sort of partition where you can have copies of V acting. In the nuclear case, then you get some things that, again, showed up at least a little bit in the previous talk, which is, so these nuclear, you get groups studied by Matsumoto and Matui, in particular, groups arising as topological full groups of one-sided subshifts of finite type. So I'm not going to formally define all of, these subshifts, but but I think Ville talked a little bit about shifts and this sort of thing. But the importance here, the consequences of the fact that in this nuclear case, we're getting these Matsumoto-Matui groups is there's a lot of theory here, right? They've proved quite a few results about the structure of these groups. In particular, a consequence is that, first of all, I think Matui proved that the commutator subgroup here of these maximal subgroups will be finitely generated and simple. The group itself, these maximal subgroups, will be of type F infinity. And using some of the theory they developed, we have methods for actually determining when, in fact, the group is its own commutator subgroup, or when the commutator subgroup has finite index, and this sort of thing. So this tells you, in fact, that we're able to sometimes determine when these maximal subgroups are simple themselves or of type F, or simple and of type F infinity, and these types of things. Right. Another sort of useful thing about these topological full groups, at least, some of the ones showing up here, is that the actions of these subgroups are what are called Rubin. They have, they're groups with Rubin actions. So, or sometimes what we call Rubin groups. Again, I won't define Rubin actions or Rubin groups, but the idea is you have a space that looks like the Cantor set, and you have some sufficiently transitive action on that space. And the importance of this is Rubin's theorem tells you So Rubin's theorem tells you that, in fact, whenever you have a group that's a Rubin group, you can fairly straightforwardly tell when they're isomorphic to each other if you have two groups that have Rubin actions. So the formal statement is that if G has a Rubin action on two spaces X and Y, then there exists a G equivariant homeomorphism from X to Y. Another way of stating this is to say that if you have two groups acting on the same space via a Rubin action, then they're isomorphic if and only if they're conjugate in the homeomorphism group of that space. So these groups are acting on Cantor set, so the Cantor set is a nice enough space, and it turns out the action is a nice enough action that you can tell whether or not they're isomorphic by figuring out if they have the possibility of being conjugate in homeo of the Cantor set. Yeah, so in other words, if I look at the types of the orbits, the types of the orbits determine the isomorphism class. So all of the things I'm saying right now are terribly imprecise, but really what we're saying is we have a method for detecting using the action on the Cantor set whether or not two of these maximal subgroups are isomorphic or not. And so using some infinite type systems, we're able to build uncountably many different types of actions of these subgroups, and correspondingly, we get uncountably many non-isomorphic maximal subgroups of V. And again, this is all heavily reliant on Rubin's theorem and the fact that these topological full groups have these sort of these locally moving actions is the word, or locally dense. Sorry, locally dense is what you want. Yeah, right. All right, so we have all these subgroups, and we have uncountably many of them. They're all coming from these type systems. So, what are some other maximal subgroups of V? Well, we know pretty much one other, T. So T turns out to be a maximal subgroup of V. And you can also take automorphic images. Meaning I can take an automorphism of V and I can look where T maps under that automorphism. So that gives you another maximal subgroup. But we, as of this moment, do not know of any others. And so, I don't know. Yeah, some of the co-authors would call this conjecture. Others would probably call it a question, because it might just be a lack of imagination at this point for building other subgroups. But yeah, the question is, if H is a maximal subgroup of V, is it true that H stabilizes some type system, or that H is some automorphic image of Thompson's group T? Yeah, and we don't know, right? So we're continuing to work on this question and try and understand what's going on here. Trying to use the fact that T is sort of characterized by a cyclic order, but the fact it preserves a cyclic order, to try and see if there are ways to detect T. Maybe you take some maximal subgroup that you found in the wild. Can you tell whether it stabilizes, a type system or if it's T? It is worth, so I'll say a few more words about that in a moment, but one thing that's worth noting is that we definitely do get infinite type systems that are giving maximal subgroups. And a really sort of standard example that one can build is if you take the ray stabilizer, but you take the ray to be irrational, meaning the sequence of zeros and ones giving you the ray does not repeat. Then what you get out of this is, yeah, you get this this infinite type system where everything off of the ray is labeled by one color, but you have to keep labeling the ray with more and more colors because of the fact that it doesn't repeat. And this is, yeah, again, one of the very standard maximal subgroups that was known to exist before our tools. So it is true that we're missing some information by only really knowing a classification of the finite type systems, for instance. But some evidence for why maybe one should believe that, the maximal subgroups fall into this dichotomy of either being type systems or something that looks like T, is the fact that we have a couple of tools for detecting whether a subgroup is or whether a subgroup is proper or not. So if we take some subgroup of V and we consider the partial action, and not on cones, but now on pairs of cones. right? So we need, just because of the action of V, we need the union of the cones to not be the full Cantor set, and we need one to not be a child of the other. But it turns out that if you're transitive on tuples, on these tuples, then in fact you must be all of V. And one fact is that T, right? Yeah, T has in fact 2 orbits on this set. So T, for instance, is a group that's going to be transitive on cones, but not too transitive on cones. That's the way to sort of formally state this in terms of partial actions. Right. Yeah. But then, again, if we remember that it's sort of standard to think about V as being this infinite symmetric group, then you can go back to these old theorems, from the 60s and 70s that tell you a lot, where people studied at length what subgroups of symmetric groups can look like. And you start spotting these theorems, like this theorem due to Cameron, which it's a long theorem here, but basically it says, if you look at a highly homogeneous action on an infinite set, but that the action is K transitive, but not K plus 1 transitive. So T here, again, remember, is 1 transitive, but not 2 transitive. Then at most K can be 3, and the subgroup in this group, which is acting highly homogeneously, has the property that either there exists a relation that's either preserving a linear order or preserving a circular order. And remember that, T is sort of our fundamental example of a group that's, setting inside V, but preserving a circular order, right? This is, one way to sort of spot T in the wild, right? Is to be looking for circular orders that are getting preserved. And so Cameron's result is telling you, that there are restrictions on how transitive actions can be, and that one should expect, right, these linear orders like Thompson's group F, although F is not maximal since it sets inside T, or these circular orders, which is going to give you T. And there are many other theorems sort of this flavor in the literature from, this time period of understanding what subgroups of infinite symmetric groups can look like. And they're all sort of saying that we should expect things that look like, T or actions that are very transitive, basically. Okay, that's all I want to say. Thank you.
Okay, thanks a lot. Yeah, so let's thank Rachel. And let me open the discussion, comments or questions. Yeah, Wille.
So I have several things, but first, you said that some of the maximal subgroups are topological full groups of one-sided subshifts of finite type.
Yeah.
My question is not specifically about maximal subgroups because I'm hearing about them for the first time. But is it known? Is it known which topological full groups of one-sided subshifts of finite type embed into each other?
So, yeah. That's a good question. I don't know the answer to that. Yeah, I don't. Yeah, I don't
The
know.
reason I'm asking is that I have a paper where I show that that you can embed one such that you can embed Thompson's V in the topological full group of some mapping class group of a two-sided subshift of finite type, and then I did the same for a full shift, but there I could only embed a sort of variant of V, and it would be very interesting for me to know sort of embeddings between these things.
Them. Right. Yeah.
So this was surprising to me to hear that actually there are these embeddings coming from maximal subgroup. I don't know anything.
Right. Yeah, I don't know, but I do think like this sort of line of reasoning is showing up a lot, of understanding which groups embed in which and this sort of thing. Again, also in this, the Boone-Higman stuff that people have been working on, again, it's a question about embedding, right, into a finitely presented simple group. And so, and people have some subgroups that they know do embed, and then the question are what are the groups that embed into the group you already know, right? So I do think people in this area are sort of thinking about these types of things, but I don't know the answer. Yeah.
Okay, and then maybe another quick question. What about 2V?
What about 2V? Like maximal subgroups of 2V?
Yes.
Yeah, we have not tried to do 2V. 2V, of course, is significantly more complicated than V in sort of a surprising way, right? Like there's a lot more things that embed in 2V.
So
but
what is 2V?
2V has the same description of V in terms of actions on the Cantor set, except now you're acting on the Cantor square. So 2V. So more generally, yeah, in V, what you do is you take, n copies of the Cantor set, and you think about it as being like a Cantor cube that you subdivide into dyadic partitions and then repiece together. And yeah, and so 2V was, yeah, sometimes this is called the Thompson groups. And is it you, Ville, that proved that every rag embeds in 2V? Is that right?
Yes.
Yeah,
But
yeah.
So I proved that every rag embeds in the topological full group of any two-sided subshift of finite type. But then,
Okay.
then 2V is a super big super group of one of these. So,
Right.
I embedded them in a much smaller group. But yes.
Yeah. I think there are some real questions whether, Yeah, 2V has a lot more setting inside of it than V does, for sure. And we have not tried to push this.
So I'm very interested in 2V because 2V is somehow, I consider it sort of a cousin of this ought A to the Z. Very often when we show something about ought A to the Z, then we show the same for 2V.
Right. Okay. So I don't know. I mean, I think possibly some of these same ideas could go through, right? Trying to put some equivalence relation on the Cantor cube.
It sounds like you're running basically a finite state machine, maybe an infinite state machine on the tree, and I guess you could run a two-sided machine.
Exactly. Yeah, it seems totally reasonable. But we have not put the effort into trying to write that down to see what works in 2V. Yeah.
All right. Other comments or questions?
I mean, can you maybe comment on how do you show this classification of finite type systems? Like into this.
I mean, really, it's about trying to figure out what types of So basically, when you're looking at these graphs, right, you have these three types of graphs. Basically what you're looking at is what are the conditions that ensure that if you attach two of the colors together, that it causes everything else to collapse. So these graphs, one thing I didn't mention is they're directed, but they're also labeled, right? They're labeled by zeros and ones, these graphs. And so the point is, what you want to see is if I take two vertices in the graph and I attach them together, but then I also attach, the two edges coming out of them together, right? What are the conditions that forces that to just collapse to nothing, basically? And it's this, right? This is what forces that to collapse to nothing. If that makes sense. Like anything else, you can, no problem. Yeah, thanks, Daniel. Anything else. So for instance, you can consider having 3 nuclei of size 1, for instance, right? But then you can glue 2 of them together and it won't, and you still have distinguished equivalence classes. And so really it was just trying to play around and figure out if I glue 2 things and I glue all corresponding outgoing edges that are labeled by 0 and 1, when does that force everything to collapse? And it's, this.
Okay, other comments or questions? That doesn't seem to be the case, so let's thank Rachel again.
Thanks.